So, the nucleation rate we derived in the last lecture is given by N0, number of sites of nucleation, Ns the number of atoms in the parent phase surrounding the nucleus, nu is the Debye frequency, which could be taken as 10 to power 13 per second. P is absorption probability, delta G star is the critical free energy, and delta GD is the activation energy for the jump from the parent phase to the product phase. Now, all of these quantities N0, Ns, nu P could be lumped into one parameter, and let me call that parameter as I0, and I can write the nucleation rate as I naught e to power minus delta G star divided by kT times e to power minus delta GD divided by kT. Now, let us understand that the temperature here is temperature less than Tr. What is the effect of undercooling? Delta T, which is T minus Tr, where Tr is the transformation temperature. So, as temperature reduces, this implies that the undercooling delta T increases, and as a result delta GV, the absolute value of the change in volume free energy, increases, or delta GV in fact becomes more negative, which means the driving force for nucleation would increase as temperature keeps decreasing below the transformation temperature. And this you can go back to the part 1 of the course to understand why delta GV would increase, the absolute value of delta GV would increase as your undercooling increases. But as a result, we can analyze what is the effect on delta G star, where we had already written delta G star to be equal to 2 gamma alpha beta divided by delta GV minus delta GS. As the undercooling increases, the quantity in the denominator would increase, and as a result delta G star would reduce. In fact, delta G star can substantially reduce as a result of increasing undercooling. Now, this would have, now what happens if delta G star substantially reduces? Look at this term containing delta G star. This would become less negative. As a result, this exponential term e to power minus delta G star divided by kT would increase, and this would have a positive impact on nucleation. That means one can expect nucleation rate should go up if my undercooling increases. However, we also need to look at the second term. What happens to this term? If we assume that delta GD is more or less a constant, then the effect of reducing temperature or increasing undercooling would result in this term reducing, because as e to power minus delta GD divided by kT, as temperature becomes smaller, this becomes more negative, and hence this term would reduce. So, we have two opposing factors to nucleation on reducing temperature or increasing undercooling. On increasing undercooling, this term increases while this term reduces, and depending on which term dominates, the nucleation rate could either increase or decrease. Now, it has already been shown in the earlier lectures in part 1, and as an example that with taking transformation of water to ice, this was an example that was taken earlier in part 1. We found that at small undercoolings, nucleation rate is small. For large undercoolings, the nucleation rate is small, while intermediate undercooling gives you larger nucleation rate. And in fact, if I were to plot I versus delta T, I would get a change in the nucleation rate with increasing undercooling in the following manner, that initially smaller nucleation rate, and as delta T is increasing, the nucleation rate goes up, and then it goes through a peak, and as the undercooling increases further, the nucleation rate starts to drop again. So, for small undercoolings we have very small nucleation rate, for large undercoolings we have again very small nucleation rate, for intermediate undercooling we can have reasonably high nucleation rates. In the case of water to ice, we had calculated this curve. Another important factor that was discussed earlier is what is called as critical undercooling, delta Tc. For an undercooling less than the critical undercooling, there is no substantial nucleation that takes place, and therefore, we cannot expect any significant phase transformation to take place. So, temperatures below that critical undercooling, there will be essentially no phase transformation in measurable time. And we had also computed this critical undercooling for different systems, including for water to ice. And in that we had assumed that there is a critical nucleation rate. If the nucleation rate is very, very small, then there will be essentially no phase transformation taking place which we can measure. And that undercooling, critical undercooling, we had taken as 10 to power 6 per meter cube per second. That is formation of 10 to power 6 nuclei in a 1 meter cube of the material in 1 second. It is a very small undercooling, and it is essentially not even possible to measure. So, if the nucleation rate is below IC, we say for all practical purposes that no transformation will take place. So, once we put these values into this expression here, putting on the left hand side the critical nucleation rate, putting values for the number of sites where nucleation can take place, number of atoms surrounding the nuclei, the absorption probability, calculating delta G star, getting delta GD, the activation energy for jump. And once you do this calculation for the water to ice system, then somewhere here let us say is IC, and this for the water to ice system would give me a delta C, which is of the order of 42 Kelvin or 42 degrees centigrade in this case, it does not matter what scale you use, because you are looking at the difference in the temperature between the temperature of transformation and the temperature at which nucleation is taking place. So, for water to transform to ice, you require an undercooling of 42 K, and this calculation was done for the case of homogeneous nucleation. So, if heterogeneous nucleation cannot take place, if there is no possibility of an heterogeneous nucleation in where you do not have any substrate on which an ice nuclei can form, then freezing of water could become very difficult. You would have to go down to minus 42 degrees centigrade in order for solidification to take place. We had also computed the peak, the highest nucleation rate, at what temperature that takes place. Let us call that as delta Tp. The peak in nucleation, at what undercooling that occurs, we found that delta Tp for homogeneous was of the order of 154 Kelvin. Then we compared this for the heterogeneous case. In the heterogeneous case, if there are substantial amount of sites where ice can nuclei heterogeneously, then one finds that nucleation of ice can take place quite easily. And in fact, if we look at the rate of nucleation in this case, one might get a curve which is shifted to the left, and this is my delta Tc heterogeneous, and this is of the order of only 6 K. So, you just have to go down a few degrees below 0 in order for water to freeze, and that is what we normally observe in our refrigerators, and that is because in our refrigerators water is solidifying through heterogeneous route. And the peak temperature, so let me call that as delta Tp heterogeneous. So, delta Tp heterogeneous is of the order of only 60 K as compared to delta Tp homogeneous. So, this was a quick summary, and before we leave this topic of nucleation rate, just also to summarize what we had discussed regarding sites for nucleation, because in this expression for nucleation rate, if I now look at I0 term, the I0 term corresponds to, has several terms N0, Ns, nu and P, in which N0, which is the number of sites where nucleation can take place. what is the density of such sites? How many sites per unit volume are present? Let us just quickly have a brief idea of this number as well. Sites for nucleation. In the case of homogeneous nucleation, all possible atomic sites in the parent phase, nucleation can take place. That in the case of metals, N0 is of the order of 10 to power 29 per meter cube. All possible atomic sites is the site for homogeneous nucleation. Now, in the case of heterogeneous, nucleation, consider for example grain boundaries. The number of sites for nucleation at grain boundaries would obviously depend on what is the density of grain boundaries, which could be related to the grain size of the material. For large grain size material, the density of grain boundary is small, hence the site for heterogeneous nucleation would be small. For very fine materials, the heterogeneous sites would be much larger. For example, consider case of copper. Let us say the grain size is about 5 micrometers. Then first figure out what is the total volume of grain boundaries present. So, volume of grain boundaries that would be present in a unit volume of the material would be inversely proportional to grain size. So, in this case 5 microns, so it is 1 upon 5 multiplied by what is the thickness of the boundary, which if we assume the thickness of the boundary to be of the order of 0.3 nanometers, then we multiplied this by 0.3 and convert this into microns by multiplying it by 10 to power minus 3, and this gives me basically the volume fraction of grain boundaries present as 6 into 10 to power minus 5. And hence N0 in the heterogeneous case would simply be this volume fraction multiplied by so many sites that are available for the homogeneous nucleation. So, that would give me the heterogeneous nucleation site, and that would be 10 to power 29 into 6 into 10 to power minus 5, and that gives me 6 into 10 to power 24 per meter cube. So, it is all of the order of 10 to power 24. Here if I have a grain size of 5 microns versus the number of sites is 10 to power 29 if I have the homogeneous nucleation. So, the sites for heterogeneous nucleation can be substantially small. In fact, for a very large grain size material like let us say 50 micrometers, the number of heterogeneous sites will further reduce by another order of magnitude. Similarly, dislocations. Similarly, if we consider dislocations, in the case of dislocations, the number of sites of nucleation will depend on what is the density of nucleation. In case of annealed material, N0 heterogeneous can be of the order of even smaller, 10 to the power 20 per meter cube. In the case of deformed material, the heterogeneous site would be much higher because deformation increases the density of dislocations, and hence N0 heterogeneous can be of the order of 10 to the power 26. For materials which are specially prepared and have very low dislocation density, the heterogeneous sites could even go down to as low as 10 to the power 12 per meter cube. So, even though heterogeneous nucleation may be an easier process as compared to homogeneous nucleation, but if there are no sites or very few, very low density of sites are available, then also the heterogeneous nucleation may become difficult. So, this summarizes what we had done regarding nucleation. If you wish, you can go back to the old lectures of part 1, where over large number of lectures all of these topics were discussed in great detail. Now, this is one aspect of phase transformation, that is nucleation. Once a nuclei forms, how fast it grows will also determine what would be the rate of overall phase transformation. So, phase transformation is going to be governed by both kinetics of nucleation as well as kinetics of growth. So, let us also now look at a brief review of the growth kinetics of the stable nucleus that gets formed. So, reviewing growth kinetics, we can look at growth kinetics as in the form of two steps that are involved. Once a stable nucleus forms, the first step may involve diffusion over large distances within the parent phase. This parent phase is what we have been calling as alpha. We are looking at alpha to beta transformation. So, beta precipitates out as a nucleus and then it starts to grow. So, there could be first diffusion within the parent phase over fairly large distances, and a second step would be atomic jump across the alpha beta interface. So, an atom has to jump from the parent alpha phase to the beta nucleus in order for the beta to grow. So, both the steps would then govern the growth kinetics. But whenever you have more than one step involved in a process, there can be systems where one of the steps is the rate controlling, and the rate controlling step is the one which is the slow step. So, let us look at some scenarios of rate controlling step. There could be a situation where there is no large distance diffusion, and this would typically occur in pure component systems, in single component system. For example, water to ice. Another example, gamma FCC phase of iron transforming to beta body centered cubic phase of iron. Again, there is no large distance diffusion of iron atoms within the gamma phase. So, no large distance diffusion. So, really the controlling step is the atomic jump over the alpha beta interface. Such a process where it is the atomic jump across the alpha beta interface that controls the growth kinetics is called as interface controlled growth. So, this is one scenario that may be there. A second scenario is that the diffusion step is the slow step, and that can occur in many alloy systems. For example, it could take place in austenite phase of steel transforming to the ferrite phase of steel. So, gamma to alpha in steel. Here large scale diffusion of carbon atoms would be involved. Such a growth kinetics where only the diffusion over large distances in the parent phase is involved in growth is called as diffusion controlled growth. Finally, there can be systems where both processes are important. Neither one is essentially dominating. This, we will call this as mixed growth. Now, why is it important to understand growth like this? Is because once we understand, let us say that it is interface control growth, then we can work out the kinetics for such a process. If we know what is that it is diffusion control growth, then we can work out what is the kinetics, and in both cases the kinetics is going to be quite different. And all of this we have already discussed in quite detail, and I am simply quickly basically reviewing the whole growth kinetics that we have done in a number of lectures in part 1. So, what I will do is in the next lecture I will review individually the interface controlled growth and diffusion controlled growth, look at how the two kinetics are different, and then we will combine the nucleation kinetics and the growth kinetics together to obtain the kinetics of overall phase transformation. So, I will stop here.